various people want to achieve various things because there are thousands of physicists who've put together the project. And everyone has their pet project. Some people are looking for a particular particle that, as I said, particles interact with each other. So if you observe a particular particle, that means you observe a particular force. And so people are interested in new forces. And the perfect example of this is this infamous Higgs boson thing, which is one of the final parts of what we call grandly the standard model of particle physics, all right? And it is a logical extension from the mathematics of the standard model that says, yes, this type of mechanism or this type of particle, this type of force must exist so that ordinary matter, protons and neutrons that make us up tonight and that make up our guacamole dip here, have some kind of mass. And there's right now no good theory other than there is this extra field permeating the universe with which particles interact and thereby gain mass. We're surrounded by an electromagnetic field right now, right? There are radio waves going through us right now. And the particle associated with that is called the photon. So with every particle, we have a wave-like nature. We have a field of waves. For the giving generation of mass, we're going to have something called the particle is the Higgs particle, and the field will be the Higgs field. And just as electromagnetic waves can travel great distances throughout the galaxy, we can see galaxies millions of light years away, the Higgs field exists, in theory, everywhere. And it's a first chance that we have, we're zooming in, we've kind of put an upper limit and a lower limit right now from the American experiment at Fermilab on what the mass of this particle could be. And if they don't beat us to it, because that's possible, we should see some kind of particle that will look like the Higgs boson, but with the physics being so possibly rich, there's no definite proof that what you see will be the Higgs boson. There might be one of 5 Higgs bosons, or it could be something else completely. So that's one big thing. Oh, the diameter of the tunnel, how wide? Like this wide. It's probably about only a little more than 3 meters. A little more than 3 meters. And inside that, you've got a metal pipe which contains all of the superconducting magnetic material. And inside that one pipe, you have 2 pipes that are about the thickness of a fire hose. And those pipes are evacuated of air, so you have a better vacuum than outer space, in fact. And protons are directed by the magnetic fields to go clockwise in one of those fire hose pipes, and counterclockwise in the other fire hose pipes. And those fire hose pipes that carry the 2 beams in opposite directions are literally only this far apart. So everything is, and the beam pipe itself, is like this kind of width, right? And the tunnel is barely wider, it's just 3 meters. But that's enough room for technicians to get in there, barely enough room. The protons themselves don't actually travel in a solid continuous beam. They actually travel like in little bunches, like a bunch of bees flying around, one behind another, all right? And the beams are focused down to about the diameter of a needle. So you have one needle of protons going clockwise, another needle of protons going counterclockwise, and the engineers are able to tweak the magnetic fields, the steering magnets, such that these 2 needles of protons hit head on. Now in each needle, which is about this long in the laboratory frame, you get about 1 billion protons. 1 billion, 1,000 million protons for those of you who prefer the English units. 1 billion protons. And out of those billion protons, the protons are so small, you may only get 10, 20 head-on collisions. And the rest of those billion protons miss each other and go back or directed back into the ring. And they get diverted maybe at some other experiment, because there are 6 different experiments located around the ring, 6 different underground caverns. It's a very tricky engineering project. Quite amazing.
When they collide,
Yes.
right, is somebody there to watch it? I mean, you said the people get inside.
Actually, I will be able to watch it. My goal is to get a remote monitoring station for New Zealand so that we can do the night shifts. We can run the night shifts for the people in Europe, and the people in Europe can run the night shifts for us. So yeah, somebody's there to see it, but vicariously they are there. They're there watching a computer screen hundreds of meters away, above ground, out of harm's way, so to speak, from radiation. But the detectors, the big soup can detectors, they are there. They suffer radiation damage. In fact, parts of them will have to be replaced after a few years. The part that New Zealand built might only last, golly, 6 months to a year, depending on how accurately those accelerator engineers can aim the beam into our experiment. Because our detectors, New Zealand detectors, hang on the outside, the very edge, and they're like the alarm detectors. They're the canaries. So if the canaries sing, you know the beam is hitting somewhere other than it should hit. It's not going right into the detector. That's what New Zealand's responsibility was in this collaboration, to put these beam radiation monitor detectors on the 2 edges, the front edge and back edge of the cylindrical soup can detector.
So what would be the mass of that proton? I mean, you say that the energy would translate to mass.
Yes.
What sort of energy level are you talking about, and what mass?
Mass increases as you go faster, right? This is, E equals mc squared, but there's another way to say that. You could say that there's also a velocity dependence, because that m could be the rest mass energy. So if I just hold a proton in my hand, it weighs, what is it now, 10 to the minus 27 kilograms? some ridiculous number like this, okay? And it's incredibly light. We think in terms of energy, so we call it about 1 GeV, 1 JeV in energy. That's the equivalent mc squared. That's the rest mass energy. We're accelerating these protons to kinetic energies of to 7,000 GeV. So 7,000 times the rest mass energy will be the energy of motion, the kinetic energy. So the rest mass will essentially be negligible. It's the kinetic energy, the energy of motion, that will be the dominant component of the energy that gets turned into mc squared and produces hundreds of particles.
There are 10 of them, and they're all banging into each other like that.
Yeah, they don't all do it at the same time. So they do it within fractions of within nanoseconds, billionths of a second of each other. And that's fast. That's, believe it or not, even though you have collisions of protons occurring just within 10 billionths of a second or 20 billionths of a second of each other, that's still slow enough for our super fast electronics to record the data, because our detectors right now, in which were frozen in design in 1998 or 1999, can take 40 million digital photographs a second. How's that for a digital camera? It's essentially the same thing as a digital camera, for the part of the detector that interests me the most. But it has 66 million pixels, but 66 megapixels. I mean, people can buy cameras for, what, 8 megapixels or even more if you're lucky.